Thank you very much. So welcome to the presentation and hello everyone. And first of all, I want to start with a small question. Who in here ever had the pleasure of working with the R programming language that's part of the title? Okay, so a couple of you, maybe that's a small bias in the people coming to the talk. But for those of you who don't know, R is a programming language that's mostly used in research for statistical computing. So by people who want to do data science, who want to do visualizations, data cleanup, do some model statistical testing, so on and so forth. And hence, it's mostly used by non-programmers. So by people who are expert in statistical domains like physics or social sciences, and who have not had any classical training in software engineering or programming, as most of you here probably have enjoyed in their past. And in practice, R provides these users with many powerful capabilities. There's a huge collection of libraries. There are many functions that R provides that are really helpful for explorative data analysis even. But on the other hand, these powerful reflective and dynamic capabilities might cause some difficulties when we try to analyze the language statically. And now you might ask, why would we even want to analyze such a language statically? So first of all, there's a lack of sophisticated static analysis tools, and I hope I don't have to tell anyone here what static tools can bring in terms of merit and support in the development cycle, but also in the analysis. We've heard a couple of talks at OOPSLA as well regarding to the benefits. And now if we want to write such a static analysis tool, we are confronted with the challenge that the language specification or the language that we're dealing with is incomplete. So we basically only have the interpreter, and the way that the language is defined in the interpreter is a way to guide us through how we should interpret some of the semantics, some of the more interesting and more esoteric edge cases that are present in the language. And now, yet again, the question is still open. Why would we even want to undergo such a challenge? The people seem happy. Well, if we look at recent studies that analyzed how well these R scripts in the wild as part of peer-reviewed and published publications do actually reproduce, we come to a very shocking number that, again, there were several studies, some of which reported slightly different percentages, but all of them are in the same range, that roughly 75 to 80% of these scripts not just don't reproduce, but usually don't even execute to completion due to various problems. And if we're tasked with such a problem, even though the language is very dynamic and we might want to analyze it dynamically, if the script doesn't even execute, well, then we're only left with the abilities that static analysis provides us with. And if now the average R researcher wants to analyze these scripts, wants to find out what's going on and wants to repair them, he's actually challenged with another problem. Now here we have such an average real-world R script. It's completely unreadable, but that's not the fault of the authors. That's probably the size of the beamer. But still, in this R script, there usually are a lot of things happening, and a lot of things happening that might not even be directly related to each other. So in this script, for example, we have various models and figures that are created, and this is completely normal in the R community, that of course you want to have several visualizations, not all of which depend on the same data set or depend on the same operations. And so with all of this happening in the same script, they are usually also hard to comprehend. So it's not just that you can just execute this script to maybe reuse a figure from the publication, or maybe just try to see and realize what the authors actually did. It's also that when you just look at the source code and try to play static analyzer yourself as a human, it's very hard to really analyze and find out what these scripts are doing. And again, if you try to reuse parts because, for example, you found a nice visualization or there was a nice statistical operation that people did in another paper, to just extract this operation is usually very difficult because it might depend on other operations done previously in the script, somewhere way above or somewhere completely else. And so again, if you want to reuse or extract some parts of the script, that's very hard. So okay, I hope I convinced many of you now, or hopefully maybe all of you, that there's merit in statically analyzing the language. And then if we try to do this, we are again tasked with the challenge of the dynamicness and all of the, for the statistical part, beneficial features that R provides. And just to give you two examples why this is hard to analyze, we have, of course, as in many interpreted languages, string-based evaluation. So you can hear these are real-world examples, and if you want to, you can look at the slides and check out the original papers that use these things. But you can, of course, use string-based evaluation, and yes, other languages have them as well, even though ours has a couple of tricky things that make it even more challenging to analyze it here. But the main thing is that these evaluations happen in many user scripts because they tend to reuse patterns that people have used before them, and they're usually used for things where they're not even necessary. So here, for example, they only read a variable. I mean, technically period could be anything, but in the context of the script, they're only trying to read a variable, and for that they construct a string that they then evaluate in the current context. And you might think that this is still sane. There are other examples which are even crazier, and this is a lot of code, so we focus on the important parts. Here we can see two functions, one of which is called pullcat, the other one is called upcat. And what upcat does, it takes the body, so the implementation of pullcat, and redefines the first expression that we see here to now read bins equals upbins, which is an open reference in the other function. So once we execute upcat, it will effectively redefine the definition of the function to now have a different implementation, which then reads upbins from the closure and will change the semantics. And of course, now this is a still very systematic example. It can do anything, whatever you like. And in general, there are many more of these examples. In R, you can redefine the assignment operator, you can redefine if, you can redefine while, you can even redefine the opening brace if you like. And so if you want to do the static analysis part, in one way or another, you have to deal with all of these things. Okay? So what did we now do in our work? So first of all, to underline the claim that the existing static analysis solutions are insufficient, we effectively looked at 31 existing implementations that in one way or another do static analysis. Those who are stricken out here are no longer maintained. And of course now we can take the time, the remaining 10 minutes of the presentation, to just look at the table and parse it. You can do that in the paper if you like. So we quickly summarize the existing findings. So analyzing all of these solutions and the capabilities they provide, we found that effectively the existing static analyzers offer no interprocedural analysis, and given that I hinted at that you can redefine the assignment operator, that you can redefine ifs and everything, in R, in the end, everything is more or less a function call, so just like ignoring them or performing summaries on these function calls already is a very, very gross over-approximation, and they usually ignore most or even all reflective and dynamic features of the language. So if some of the things like the body assignment I've shown you earlier happens, they just give up or do some assumptions and then continue their analysis. And in general, another problem is that most of these tools, again, they don't even provide a way to extend on the analysis, so they calculate some results and then they use it internally, and the only thing they expose to the user is effectively a short information about, hey, this variable is global, or hey, this function does this and that, and there's no way to really extend on these existing capabilities, and many more. And with our work, we effectively try to address all of these things in one way or another. So how does the analysis that we actually conduct work? So we don't have the time to go into the gritty details, and again, I point you to the paper for this, but on a very high level, we follow a pipeline architecture where we, of course, first parse the R code, then we normalize it to abstract away from version dependencies and some of the nitty-gritty details that the R language has. Then we perform the data flow analysis. I have another slide for that to go into a little bit more detail what this magic stack implies. And then we can use these results to do further analyses. And as a proof of concept in the paper, we implemented a backward program slicer. Again, I will talk briefly about that later. So effectively a way to condense the scripts to just focus on a singular figure or on a singular statistical test, for example, right? But in general, the pipeline architecture that we provide is general enough that you can theoretically extend it with many more things. So once we have the data flow and control flow graph that we generate, we do many more analyses that are possible. For example, a dependency analysis to find out which figures are created, where statistical tests happen, what library versions are used, and so on and so forth. But now, how does the actual core analysis that we provide work? Well, the challenge with R is, again, that there are so many reflective features that intertwine with each other. There is lazy evaluation, which may entail side effects. Again, any operator may be redefined, so you need full context information to be even weakly aware of what could happen in a certain scenario. And we do this by taking a simple piece of R code, transforming it into the normalized AST. Again, you don't have to follow and read all of that. This is just the simplified normalized AST of this code above. And what we then do is we effectively do a tree walking interpreter approach where we take the AST, do a stateful fold, and incrementally construct the data and control flow information of the program by repeatedly applying all of the passes that we essentially have, intertwining data flow, control flow, and any other abstraction all the time to be able to even find out what various operations in the program are doing or are maybe able to do. And hence, for example, here we have the assignment to the @ symbol, which is represented in the normalized AST over here. And for this, we start by building a small data flow graph, which is visualized here. We track additional information, and then we subsequently incrementally construct the data flow graph, doing the fixed point iterations over the tree structure as well by combining the results. And here you can see the add graph again. This is the body of the function, stitching effectively the subgraphs of each subtree together until we reach the final data flow graph of the program. And again, this is a very, very brief summary of what we actually do in the paper and what we actually do in the work. So again, if you're interested in that, please check out the paper, right? And now to get to one real-world application of what we can use this analysis for, I already hinted at the static program slicing approach. So if we again go back to our wonderful R script, which does several visualizations and several modeling operations, what we can now do if we take on the hat of a researcher and we are, for example, just interested in a single figure or in a single statistical test, we can pick this figure or this statistical test, and the program slicer will reduce the script to just the parts which are relevant to produce this specific figure. Okay? And so in this scenario, now this is the real-world example, but again, it's hard to read on the beamer. In the real world, when we do this, we achieve average reductions of 80 to 90%. So if you're aware of program slicing, these numbers are really high, and this again underlines how interestingly written and exploratively written maybe these scripts are. But what this number means effectively is when we are interested in just a single figure in the script, on average, we only need 10 to 20% of the original program, and that again speaks to how it may be easier to understand these programs than if you're only focusing on a specific figure. There's also an extension for Visual Studio Code and Positron that you can use, but we stick to the research part here. So in general, we now have this analysis, but without a normal or a fundamental specification of the R language, it's very hard to know whether what we're doing is actually correct, right? I'm just telling you that we have 80 to 90% reductions, but the slice could just be wrong, right? And so we conducted an extensive evaluation that I'm now showing in a simplified form because we did multiple steps to at least empirically underline the correctness and the performance of our approach. So simplified, what we did is we took all R packages on CRAN, which is the comprehensive R archive network that were available at the time, and we did took a couple of R artifacts. We conducted our analysis. We measured timing information. Of course, we did that repeatedly. Then we sampled slicing points in these scripts, conducted the program slicing, again measured the timing and the size reduction, and from there on out did the performance evaluation. In here, there's still no correctness evaluation, so this is now just the performance part, where we measured the speed of our analysis and came to roughly 150 milliseconds on average per package and 580 milliseconds per script file, which is mostly due to the fact not that script files are technically more complex, but they're usually longer compared to the average package file. And again, the slicing reduction I was referring to earlier, here we achieved an average reduction of 88%, but we still don't know whether the slices are correct, or the data flow graph in that matter. So what we did, we did multiple correctness evaluations, but just to show you one of them, you can find the others in the paper. We took a couple of these scripts. We tried to find scripts which were already executable or which we transformed manually into an executable state that were also deterministic. In there, we labeled points of interest according to the paper. So we looked at the paper, found the visualizations, and labeled them within the script under the assumption that these are possible the points that real-world researchers would be interested in slicing for. Then we ran an automated instrumentation execution to effectively arrive at the ground truth, so what the script is supposed to execute in a given scenario. And then we took the same scripts, the same point of interests, conducted our analysis, computed the slices, reran the slices to check whether the output for the figure or statistical test in question is identical. And if it is identical, then we know that at least the slice contains all of the information that is required to reproduce the same output. But again, we could just return the full program and would still be fine because the full program is always the trivial slice. So what we then did with the correct slices is we shrunk these slices to find the minimal subset of slices, and I'm speeding up to get to the point. What we found in the end is that of these correct slices, we achieved roughly 99.7% of correct slices, which means for 99.7% of these points of interest, we produce the identical result to the complete script execution. And precision-wise, we achieve a precision of roughly 94%, which means if the resulting slice, let's say, has 50 lines, we usually only have 2 to 3 lines that are superfluous and redundant in some way that we included just to be safe. So, and we are also reducing the runtime of the actual script. And we also compared it to the state of art, but again, for the sake of time, you can check this in the paper. So just to recap, we looked at the state of the art. We propose a new data flow analysis framework. We propose a program slicer that can then be used to make the script more easily comprehensible. And if you're interested in more of these things, here's a link to the project, which is open source, and a link to the paper. And below there is my email. So if you're interested, feel free to reach out. And with that, thank you.